All right, so we are delighted to have Professor Singamaneni from University of Texas, El Paso. My apologies, almost got it wrong. From University of Texas at El Paso, giving our final 2DCC seminar of the semester. So please take it away whenever you are ready.
Yeah, thank you very much, Stephanie, for your kind introduction and invitation. I'm happy to share some of our recent findings from our group. So our group mainly focuses on quantum magnets and materials, how we can use them for potential exploring for physical properties, particularly magnetic and energy-related properties. So before I dive deep, here is an announcement. Our department secured independent PhD program a year ago, particularly on quantum science and information. I know Penn State has a lot of students. Please send some of them over to here. I appreciate it. Thank you very much. All right, moving further. So today I am presenting some of the work done by our students. Luis, now he is a director's postdoc at Los Alamos National Lab, Ruby at Rice University doing PhD, and Hector is at Stanford University doing his PhD, and Sudeshna, a current postdoc in our group. So this slide highlights some of our on-campus collaborators as well as collaborators from outside campus and a bunch of funding agencies, particularly the NSF, ACSPRF, and LDRD project from Pacific Northwestern National Lab. So here is a plan of my talk. I anticipated that there are a bunch of students around, so I thought it's a good idea to spend quality time on providing some background and motivation and introducing some materials and methods. And I will spend chunk of my time in sharing our recent findings related to intercalation, pressure, photo excitation, and if I have time, I will spend some time on the catalysis part of our research, and I will end my talk by providing a bunch of conclusions. Moving further, so we all know why we should care about doing research on magnetic materials, particularly have a lot of applications related to data storage, and this is the storage mechanism we have been using traditionally, and people started moving away from traditional data storage devices, particularly after having a lot of limitations. And the most recent one is, Google Data Cloud, many other platforms, even the small children. But for example, my boys who are in third grade and 10th grade, they use cloud, Google Cloud, to store their pictures and files, things like that. The point to note here as scientists and engineers, right? So there is a growing gap between amount of data we generate and the data storage devices, and the gap should be minimized, that should be addressed. So that's where I think the scientists and engineers come up with the solid plans and explore ideas in discovering new materials, new magnets, studying their properties, and see if we can use them for potential data storage device applications. With that motivation in mind, researchers around the world started looking for new magnets. For example, in 2017, two independent groups, one from Seattle, another from Berkeley, they have shown that it is possible to realize 2D magnets experimentally. Until then, Merman-Wagner theorem prohibits the realization of 2D magnets experimentally, particularly because of small magnetic anisotropy, and that is inferior or a low number compared to thermal energy. And these two independent groups have shown that it is possible to realize 2D ferromagnetism on monolayers of chromium iodide and chromium germanium telluride. And particularly having this work published in 2017 back to back, faculty members around the country and other parts of the world started doing research on 2D van der Waals magnetic materials. not only from interesting physics point of view, also looking at low dissipation magnetic devices and their ultra compact nature, so that we can use them for potential applications down the road, let's say 5 to 10 years from now. So that motivated our group to get into the field of quasi 2D magnetism. And there are some educational sides why we should care about 2D materials versus 3D materials. For instance, 2D materials offer high surface to volume ratio, and we can seamlessly heterostructure them with the different materials because we have a weaker interfacial coupling and almost negligible dangling bonds, things like that. And out of all, the one that caught our attention for magnetic property study is the magnetic properties of these materials are often exchange, particularly the exchange interactions, they're anisotropic. It means that, so if you rotate the crystal or a layer, so we say strong anisotropic behavior compared to 3D counterparts. Moving further, so for example, you can take a look at this periodic table here, and we can select bunch of cations, bunch of anions, and one can make layered magnets. For instance, in the recent past, people heavily focused on chromium halide compounds, and recently many people started looking at multiferroic materials like nickel halides, nickel bromide, nickel iodide, cobalt iodide, and their alloys. Moving further, this slide provides kind of timeline where, in 2017, after first 2D ferromagnetism was reported, and people started playing a lot of, tricks to control and, manipulate their magnetic properties. For example, in 2018, so you see people started applying electric pulses and controlling their magnetism and magnetoresistance. Particularly, this is very important for device applications. And 2019, they started applying pressure and changing the stacking geometry and studying their properties. During a COVID time, people did not stop looking at these properties. They went ahead and studied the skyrmions, new spin structures, new spin waves. Right around that time, we were able to publish one of the earlier articles where we have shown that one can apply optical pulses and study control their magnetic properties. And in the recent past, people started twisting these magnetic layers and controlling their properties. Right when we are trying to get into this field, there are a bunch of review articles appeared, and the one that caught our attention was done by Ken Butch at Boston College, and he has showed some kind of guidance, right, saying that okay, look, there are plenty of materials out there, but these materials offer a lot of interesting opportunities. For example, one can apply gating, one can do proximity, and one can do Moire engineering. But the one that did not explore much at that time was applying light or shining light and controlling their properties. So that's where we started our work, looking at how one can tune and control the magnetic properties and interactions in these quasi 2D layered magnets, right? So, for instance, so in the past, several people reported how optical pulses, for example, your department has expert Venkat on this optical control magnetism, right? So by shining light on, for example, antiferromagnetic crystal, 3D crystal, you can convert antiferromagnetic crystal into ferromagnetic crystal. So basically what you are doing is we are tuning the minima of the potential well here. And that is the basis for changing the magnetic properties of this material, and is having potential applications ranging across frequencies from gigahertz to terahertz to femtosecond range. Right, so you can have a lot of applications, for example, imaging, communication, computing. So one can have a lot of applications by employing optical pulses in controlling the properties of these magnetic materials. This slide provides, the best qualities of, van der Waals crystals and optical stimuli. For example, optical stimuli is is a clean, contactless, non-invasive, and particularly it requires very low power when compared to electrical pulses. And this is quite rapid compared to electrical stimulation. And these materials offer exciting properties, particularly they're optical and magnetically active. And these materials have strong light spin coupling or light magnetism coupling. And the unexplored properties of these materials by then are spin lattice coupling and how one can tune magnetic anisotropy and magnetic order. So we looked some of them in our work. So second part of my talk deals with how these layered quantum materials can be used for potential applications. For example, so moly sulfide, though it's not magnetically active, but it's optically, electrical, and catalytically active. And people have shown that this material can be used for battery applications, supercapacitors, oxygen evolution, and hydrogen evolution reaction by doing a lot of material engineering, either by doping or defects, applying strain, changing the layer structure, things like that. Okay. Out of all, the most exciting aspect of this material is how to produce hydrogen cheaply by not using platinum group elements, so that we can address the limitation of platinum, which is super expensive and it's getting more and more rare, right? So people have shown that it is possible to use this material as a secondary candidate to produce hydrogen cheaply. But the problem is there is a limited knowledge available on what happens to the hydrogen evolution reaction when the reaction is taking place. So there we entered into the field. So we contributed to some extent that in designing the in situ capabilities and track hydrogen evolution reaction as the reaction takes place. I will spend some time on it in the second part of my talk. So this slide provides a bunch of techniques we used. For example, in our group, we have 3 magnetometers. So we can weigh the parameter space by changing temperature, magnetic field, shining light, pressure, rotating. And we have electron spin resonance spectrometer on campus. And also we use capabilities at National High Mag Lab as well as Pacific Northwestern National Lab. And at Los Alamos and Argonne National Lab, we use ultra-fast optical pump probe techniques. And at NIST, we have a collaborator who can do measurements, Raman measurements as a function of temperature and magnetic field. And we have a bunch of theory collaborators who can provide theoretical calculations to support our experimental findings, both on campus and around the country and beyond. So I start with this layered material, chromium halide. So as you can see, these are layer structures. And by changing halogen, as you can see from iodine to bromine to chlorine, so you can see that we can vary the magnetic properties of this material, particularly the Curie temperature varies from 68 Kelvin to 33 Kelvin. And you see there is a nil phase, an antiferromagnetic phase at about 14 Kelvin. And these materials also change their electrical properties as well as you change a valence halogen element. And on top of that, these materials show record high values of excitonic binding energies, particularly the giant GM1 splitting and giant K response. These properties enable us to apply light in controlling and manipulating the magnetic properties of these materials. Okay. Another class of compounds we looked at, these are magnetic dichalcogenides, for example, manganese silicon telluride compounds. So recently, this compound received a great deal of attention, particularly for its unconventional CMR, that is a colossal magnetoresistance. So this compound shows unconventional CMR when we apply magnetic field along hard axis. In general, compounds exhibit CMR when you apply magnetic field along easy axis. And another interesting observation people made recently is though the orbital angular momentum is almost zero, this material shows unexpected magnetic behavior anisotropic behavior about 13 Tesla. And this material shows ferrimagnetism below 78 Kelvin due to uncompensated magnetic moment. So there are many interesting properties that this compound showed, and people try to understand through different ways why this compound is quite interesting, how to tune the magnetic interactions, things like that. So going further, so here is a hypothesis for photo excitation of these crystals. We take a crystal and the crystal has a ground state and excited state or charge transition state, and we have a bunch of exchange interactions. So we tune the minima of the potential well. So basically by choosing, the transitions here, whichever are prominently strong upon photo excitation, and track the response by applying pulses at the different time scales. For example, here I show how we do pump probe measurements. So Venkat in your department is an expert on this topic. So what we do is we pump the crystal and we disturb the crystal and we probe the response by shining another pulse. And another aspect of our research is, how intercalation of these materials can tune the magnetic properties, particularly by taking advantage of the interlayer gap between any two layers. So we invested our time and effort recently on this topic as well. So I'm happy to present some of our recent work here. So the first project is on how one can tune the magnetic properties of these materials by intercalating this material using organic molecule. For example, we started with tetrabutyl ammonia cation here, and we intercalated that between the two iron germanium telluride layers. Okay, so we did bunch of magnetic measurements. Okay, and that is before we intercalated the compound with the TBA plus, and after. So the one that caught our attention particularly, I would like to draw your attention on this particular figure, you see. So in the pristine case, this compound is a paramagnet at room temperature. Upon intercalation, you see the magnetic behavior of this compound changed, and you see hysteretic behavior, which is absent in the pristine case. And even within the hysteretic behavior, you see step-like feature. That means that you have another ferromagnetic phase that is created after this compound is intercalated with the TBA plus. Okay, and we have done temperature dependent isothermal measurements, and as you can see that until 350 K, this compound showed hysteretic behavior. So that shows that upon intercalation, this compound enhanced its ferromagnetic phase from 150 Kelvin into almost 350 Kelvin. To better understand this, we expanded these measurements as a function of temperature and magnetic field using Raman spectroscopy. So our collaborator Satnish conducted these measurements, and we computed how Raman shift is changing as a function of temperature. From Raman shift, we computed the spin phonon coupling, and we find that Raman measurement showed a strong electronic doping effect, and these measurements were complemented by theoretical calculations, and the calculations show that so there's a substantial number of electrons from TBA plus moved to nearby FGT layers, but for example, you say about 0.16 to 0.1 electrons per layer. For iron, for tellurium is much higher, is 0.51 to 0.7 electron per layer. And we expanded this work to another independent layered compound, that is chromium germanium telluride. So we used the same intercalant, TBA plus, which is known as a very strong electron donor. And we conducted measurements in the pristine case, and it showed a typical Curie behavior with the Curie temperature about 66 Kelvin. As you can see that in the pristine case, the Curie temperature is about 66 Kelvin. It is consistent with the reported value. But upon intercalation, you see a step-like behavior in magnetization versus temperature graph. And after taking the first derivative of it, so you see, along with the pristine Curie temperature, so we observed two more additional magnetic phases whose temperatures are at 178 Kelvin and 204 Kelvin. So these were absent in the pristine case. And we did a bunch of as a function of temperature, we collected isothermal measurements, and you see that up to about 200 Kelvin, we see non-linear behavior. So that clearly shows that intercalation enhance or introduce new high temperature magnetic phases. And our collaborators at Argonne National Lab did STEMG imaging on the pristine as well as intercalated crystal, and they measured that along c-axis, the layer gap increased along c-axis, whereas along ab-axis, everything is same as pristine case. So that shows that there is an indication that the gap increased. It means that the layers were intercalated with the TBA plus. And our collaborators at NIST conducted temperature-dependent Raman, and they extrapolated spin lattice coupling, and they found that there is a strong electron donating effect from TBA plus. And these experimental findings were supported by DFT calculations, saying that there is electron doping, there is a charge transfer from TBA to chromium here in this case. And that led to the semiconducting to metallic transition, particularly the one we saw at 204 Kelvin. And moving on, so we also apply pressure on these layered magnets, and we vary the pressure, particularly the low pressure range from 0 to 1 gigapascal. That's what we have in our group. And we observed that Curie temperature decreased and the magnetization decreased as a function of increasing pressure. And these measurements were complemented by theoretical calculations. And as you can see that the magnetic anisotropic energy is changing as a function of pressure. This is the one we did on chromium silicon telluride layered compound whose Curie temperature is about 32 Kelvin. And then we changed chromium into manganese, as you can see that. So the magnetization decreased as a function of increasing pressure. However, the Curie temperature starts increasing as we increase the pressure. So exactly similar compound, but the Curie temperature behavior as a function of pressure is completely different from the previous compound. And our collaborators did some calculations on pressure-dependent magnetic properties, and they have seen that the first neighbor is varying, particularly the exchange interaction of a first neighbor, the J component changing as a function of pressure, as well as magnetoanisotropic energy. And this work was, cited by other group members, from other campuses, and they have gone up to about 20, 30 gigapascal, and they were able to increase Curie temperature further up. And that motivated us to go for much higher pressures on another independent compound. For example, take a look at this compound, this iron germanium telluride. This is one of the compounds where people study heavily because this compound shows relatively very high Curie temperatures above 150 Kelvin until 300 Kelvin just by changing the iron vacancies here. So that's why this compound is interesting. So in our lab, we did pressure dependent magnetic measurements. As you can see, the magnetization starts decreasing as well as Curie temperature up to about 1.2 gigapascal. And we went to Argonne National Lab and conducted XMCD measurements as a function of pressure. So as you can see, up to about 23 gigapascal, the XMCD signal starts decreasing in the ferromagnetic phase. So it means that the ferromagnetism did not increase as a function of increasing pressure in this compound, unlike earlier compound where Curie temperature increased with increasing pressure. So to complement these findings, so at Air Force Lab, as a part of our summer faculty program, so myself and my students spent one summer month there. So, and we conducted Raman measurements as a function of pressure. As you can see at atmospheric pressure, so it's a beautiful Raman spectra. So as you start applying pressure, so you see that Raman signals disappeared, okay? And it disappeared completely at about 13 gigapascal. And then after the cell is decompressed, we get back those Raman signals. So it means that we don't destroy the sample upon applying pressure, so we get back signals back to the normal position after decompressing the cell. It means that there is something really something going on, not going from amorphizing the sample. So we are not killing the crystallinity of the material upon applying the pressure, but there's something more is happening to this compound. So we plotted the frequency shifts as a function of pressure, and you see the optical images. So when the measurement was taken at atmospheric pressure, so you see the optical image of the crystal, and upon applying the pressure about 7.6 gigapascal, so you see the optical image changes, and upon decompressing the cell, so we started getting back the crystal back to the normal. So it means that so one can use pressure as a tuning knob to control and manipulate the magnetic properties of these materials. So our theory group is doing some calculations on this part. So very soon, hopefully we will complete these measurements and submit for publication. So going further, so this slide onwards, I'll spend some time in presenting our work related to optical control of the magnetic properties of these materials. So as you can see here, this is the optical absorption spectra of chromium iodide compound, and it shows 4 optical transitions. And out of 4, we took 2 strong transitions. One is a ligand to metal charge transition 1, another one is ligand to metal charge transition 2. And we conducted magnetization measurements on this compound, and you see that the black curve shows the pristine behavior of chromium iodide at 50 Kelvin. It is a ferromagnetic phase. And upon shining the light with the 2 different wavelengths separately and 2 different crystals, so you see the magnetization, particularly the saturation magnetization, jumped up in both cases. And that is consistently observed in the temperature-dependent magnetization as well. So you see upon photoexcitation of this compound, the saturation magnetization went up upon shining light with the 2 independent excitations, 1.93 electron volt and 2.7 electron volt. However, we saw that Curie temperature remained unchanged in both cases. So only the saturation magnetization increased upon photoexcitation. To dig deeper, so we conducted electron spin resonance measurements by shining light on it. So here we took LED. So we took spectra when LED is off, and we took spectra when LED is on, and then we recorded a signal when LED is off again as a function of temperature from 60 Kelvin to 100 Kelvin. And we measured how the signal intensity changes as a function of time here. So we did analyze the data, and then we extracted some numbers. These numbers are important here. The numbers are G value that shows how strong is the spin-orbit coupling. And we saw that number increased. That means that the spin-orbit coupling of this compound increased upon photoexcitation. And another number is delta HPP, that is the peak-to-peak line width of the signal. And this line width also increased. That signifies that we are changing the interactions at the local chromium 3+. So essentially what's happening, that I'm going to provide some proof as you go further. So when we shine light on this crystal has a chromium 3+ only. When we shine light on it and it photodopes, and then it converts part of chromium 3+ into chromium 2+. So now we have 2 sub-spin systems. One is due to chromium 3+, another one is due to chromium 2+. The interaction between these 2 spin systems can lead to change in the local magnetic interactions. And we analyze the data using the formalism reported in the past. Okay, and we extracted the numbers, particularly a change in super exchange interactions before and after photo excitation for both these two transitions, LMCT1 and LMCT2. So we estimated these numbers before excitation and after excitation, and clearly we saw increase in super exchange interactions of these two transitions on this compound. So the increase in the super exchange interaction explains why there is an increase in the saturation magnetization of this compound upon photoexcitation. So somebody did calculations on this compound before and after photoexcitation, and they gave us this kind of picture, and this picture shows that so there is a chromium 2 plus valence is formed near to the conduction band. So chromium 2 plus is giant dollar active ion, and chromium 3 plus is giant dollar inactive ion. And our theory group estimated a spin orbit coupling number through G values, and these numbers match with our experimental values. So that helped us in constructing this kind of cartoon schematic diagram. So essentially, upon photo excitation, we are creating chromium 2 plus, whose electron spin is more than chromium 3 plus. For chromium 3 plus is 3.5 and chromium 2 plus is 2. So we are increasing the spin amount by shining light on this compound, and the interaction between chromium 2 plus and 3 plus cause enhancing the magnetic saturation upon photoexcitation of this compound. So we went ahead and did a bunch of experiments at Los Alamos National Lab. These are pump probe measurements. So we took this crystal and we measured time resolved Mach signal above Curie temperature as well as below Curie temperature. And as you can see, the coherent oscillations here in the ferromagnetic phase by changing the helicity of the shine light. So we see the change, sign flips. Okay, it means that we are looking at the ferromagnetic phase of this compound, and that is not new, and it is well established. Okay, so what we did, we took spectral density from this time resolved signal, okay, in the paramagnetic phase, and we saw two Raman modes, A1G and A2G mode in the paramagnetic phase. So here A1G mode is defined as, that is the AB plane oscillation, and A2G mode is defined as C-axis oscillations. Okay, and that is the case in the paramagnetic phase. And when we did the same experiment by flipping the helicity of this laser pump pulse, and we did the same exercise, and we took spectral density, and we see that upon flipping the helicity, so the intensity of these two modes remain practically same, both A1G mode and A2G mode. Whenever we conducted these measurements in the ferromagnetic phase and went to the same exercise, so the A2G mode intensity drastically decreased when we flipped sigma plus into sigma minus, whereas the intensity of A1G mode practically remains same. So it means that A2G mode is strong function of the magnetic phase of this material. So what we did next, we tracked the intensity ratio of A2G mode between sigma plus and sigma minus as a function of temperature, and that is plotted here. So you see, this is the phonon helicity ratio, that is A2G as a function of temperature. Okay, and this is A1G phonon helicity ratio. You see that the intensity of this A1G phonon mode is more or less practically independent of temperature. Okay, our theory collaborators simulated this pattern by incorporating the magnetostriction effect on this compound upon photoexcitation. So this trend mimics the temperature-dependent magnetization of this compound, and it follows the temperature-dependent helicity ratio. Okay, so both go hand in hand. That shows that there is strong interaction between the electron spins of this compound and phonon vibrations. So that tells us that we are looking at strong spin phonon coupling through magnetostriction effect. So we expanded this work to another independent compound, that is the manganese silicon telluride. And similarly, we collected differential reflectivity signals as a function of temperature across Curie temperature at a different power, so that we make sure we don't kill the crystal by shining by pumping more power to into it. So we took optimized power so that we don't destroy our crystal. Okay, we extracted a bunch of numbers, and the most important one is the frequency, how it varies as a function of temperature. So upon taking the differential reflectivity data, and then we extracted the phonon frequency intensity, particularly, the phonon peak shift here. As you can see that how the phonon is shifting as a function of temperature. The trend is shown on left y-axis, and the right y-axis we show a temperature-dependent magnetization. Okay, so they go hand in hand, and that is the Q temperature is about 75 Kelvin or 74 Kelvin. So that shows that these materials show strong spin phonon coupling, and we extracted that information by applying optical pump probe pulse, and most likely that is due to there is a magnetostriction or magnetoelastic coupling. There's a debate going on in the literature. So we believe that there is a magnetoelastic coupling. This material provides upon photoexcitation. Basically, we are distorting the crystal, expanding the crystal upon photoexcitation. So we are conducting additional measurements on another important layered antiferromagnetic material, that is a chromium sulfur bromide. And here I show our initial data. So here you see this is the electron spin resonance signal. Before we shine light on this crystal, we use a UV lamp about 280 nanometer, and then we shine light on this crystal and then see how electron spin resonance signals evolve as the time progresses upon photoexciting this crystal. And after about 10 seconds, the signal comes back to its original pristine state. So during that during this time, so you see how the signal narrows, how signal moves towards the original position, and the shape of the signal also changes. So we extracted all that information as a function of temperature, time, angle, and we are putting together and see what exactly is happening between the light we shine and the the local optical phonon we generate in this material. That could tell us that there is something happening at the chromium side by interacting with applied photons. So that brings us to the second part of my talk. So second part of our talk deals with how using in situ capabilities, particularly electron spin resonance spectroscopy, we can track energy reactions while the reaction is going on. So for example, we are investing our efforts in the case of battery materials, how battery performs, how battery fails while the battery is the reaction is taking place. And similarly, so we are investing our efforts in better understanding photocatalysis, in producing hydrogen through water splitting upon shining light. And we are using the same knowledge to track the battery reactions by developing in situ probes that is compatible with the magnetometers. So I will present some of our earlier results to demonstrate our recent efforts on this research thrust. Okay, for instance, you can take a look at this slide. This slide is busy, but I will take you through slowly. So for instance, this slide talks about how one can use in situ electron spin resonance capabilities to track hydrogen evolution reaction in producing hydrogen cheaply through water splitting by using molysulfide as a cheap earth-abundant electrocatalyst. For example, you take a look at this top left figure. So this is the big beaker. So we set up electrodes and we apply voltage, and then and um, and we have molysulfide electrocatalyst, and then we see gas is coming up. That is a bubble, gas bubble, hydrogen gas, and we independently confirm that it's hydrogen gas, is no other gas, by connecting this with HPLC. So we tracked current versus voltage plots, and we saw the number that is close to where we expect to get for hydrogen evolution reaction. And we mimic the same experiment by shrinking this beaker, big size beaker, into millimeter size beaker here. So we put all the electrodes inside a millimeter size beaker, and we use molysulfide catalyst, and we produce gas, that is hydrogen gas, and we tracked its current versus voltage behavior, and that number is matching with the reported number. And going further, so you see electron spin resonance signals before and after the reaction. Okay, so you see two distinct EPR signals, and that is well known, as people already reported what happens to this compound when electrocatalyst, before electrocatalyst takes place. What is unknown is what happens to the signals during the reaction. Okay, so this plot shows electron spin resonance signals as we change the potential from 0 millivolt up to 600 millivolt, and you see the intensity of the signal varies strongly as a function of electric potential. So that shows that we are changing the intensity of active species which contain unpaired electron spins. So basically, the signals like this, there's a combination of moly anticides as well as sulfur vacancies. So we simulated the signal and we extracted the information about what exactly is going on in this in situ EPR experiment, and what are the catalytically active sites that lead to hydrogen production. And our collaborators did theoretical calculations, and they have shown that it is the free energy as a function of electrode potential is changing, and as a result of that, you are changing the intensity of the signal or magnetic moment of the signal that is plotted on the right y-axis. So though their curvature is different, but their trend is similar. So you see the structures that they consider while computing these free energies. The point to note is that by using a combination of in situ electron spin resonance capabilities plus electrochemistry plus DFT calculation, we can clearly establish what exactly is happening during a hydrogen evolution reaction. So going further, we collaborated with one of your faculty members, Professor Teron. So they were doing experiments on defective boron nitride material in producing hydrogen gas. And they did a bunch of experiments like a photoluminescence, theoretical calculation, all other measurements. And they were looking for independent support of what exactly the reason for their superior hydrogen evolution behavior when they were doing measurements on defective boron nitride compound. And we did electron spin resonance measurements, and we extracted the numbers, and we found that nitrogen vacancy sites, in other words, boron-rich vacancies, they are responsible for the superior hydrogen evolution reaction of this defective boron nitride compounds. Similarly, our campus, the chemistry department faculty, they have been working with iron oxide materials for oxygen evolution reaction. So they took two independent iron oxide compounds, and one iron oxide compound showed much superior oxygen evolution reaction compared to other iron oxide compound. And they approached us, and we used our expertise and magnetism, and we found that one compound has higher spin polarization compared to another compound. And using those measurements, coupled with their own measurements, and they constructed a mechanism why these iron oxide compounds show superior oxygen evolution reaction. And that established the fact that one can employ spin probes to detect energy reaction while they're taking place. So there I conclude my presentation. And so these are conclusions. And the most important conclusions are the one, by taking advantage of the layered nature of these materials, so we can control and manipulate the magnetic properties of the layered van der Waals quasi-2D magnets upon photoexcitation. And we have shown that on 3 or 4 independent compounds such as chromium iodide, chromium chloride, and manganese silicon telluride, as well as chromium sulfur bromide. We also applied pressure as a tuning knob, and we have shown that it is possible to manipulate the Curie temperature as well as magnetization on this compound by applying pressure from 0 to almost 25 gigapascal. And out of all, and we find that intercalation is a very versatile, easy route to drastically change the magnetic properties of these layered quantum materials. And one can enhance the Curie temperature from 150 Kelvin to 350 Kelvin, and one can induce new magnetic phases on these layered quantum materials. So using simple non-magnetic organic intercalation like TBA plus. So currently we are expanding this work to sodium, potassium, rubidium, etc. Lastly, so I also have convinced you that it is possible to develop and apply spin-based techniques to track energy reactions while the reaction is taking place, particularly for hydrogen evolution reaction and oxygen evolution reaction. There I stop my talk. Thank you very much for your kind attention, and I am happy to answer your questions if any. Thank you one more time.
All right, we have some time for questions. So if you are online and want to ask a question, you can raise your hand, or you can type it in the chat, or you can just unmute and ask it. So online people, go ahead and do that. And in person, are there any questions? Yeah.
Yes, Professor Sikamanini, I'm very interested about your results on the hydrogen evolution of molybdenite and the tracking you did with the EPR. So as far as I understand, you look at the dynamics of the ampere electron in the vacancy, and that gives you information about the reaction of the waters and hydrogen evolution, right?
Right.
So what did you learn? What is the mechanism that you have in mind? And what did you learn about that mechanism through the lens of EPR?
All right. I did not disclose that part of the information because we are writing a manuscript, but in simple words, I'm going to tell you this. So we chose molysulfide as a different crystallite size, and we observed the lowest crystallite compound shows highest amount of hydrogen gas, and we tracked that using advanced electron spin resonance measurements. And what we found was that the lowest crystallite size has large number of sulfur vacancies, and though that compound has other paramagnetic centers like moly 3 plus or oxygen coordinated, but only the sulfur vacancy related active sites could lead to higher hydrogen evolution reaction. So that's all I can tell now. But after maybe 2 weeks, you will see our manuscript online ConMed. So there we are going to provide almost all the details. I hope that answered your question.
Well, it doesn't, but it gives me hope that I will learn at some point the answer to the question. Thank you.
Yeah.
The other thing is that, so probably a similar question, and I assume I will get a similar answer, but for the case of the boron nitride, you just said that the boron-rich sites are more efficient for hydrogen evolution, right?
Yes.
Is that correct? So again, why? what is your hunch for the explanation of that?
So yeah, I don't have any more explanation other than what I provided there. So we could not continue further by changing the crystallite size. So we changed the defect. Terran's group changed the defect concentration, and so that's a good question. I think we didn't have a chance to pursue that further. So maybe, yeah, that's the reason I think I wanted to visit your campus and talk to Professor Teron to see whether he is continuing that work further so that we can come back and try to address those fundamental questions. Yeah, sorry. So I don't have much more information than I already provided. The work was already, published in materials today.
Sure. No, thank you.
Yeah.
Definitely, it's very interesting information. Thank you.
Yeah.
All right. Other questions? Anything online, Chelsea? Any other questions from in-person people? All right. If not, let us thank the speaker one more time for an excellent talk. Thank you so much for coming. We really appreciate it.
Yeah, thank you very much, Stephanie, and say hi to our friends, and particularly George, Joan, and Venkat.
Will do.
Yeah, so they were our invited speakers at MRS. So we had a nice time at MRS meeting.
Awesome.
And Nasim,
Fantastic.
yeah, Nasim and myself, we co-organized a symposium in 2019.
Oh, awesome. We'll say hi to everyone. Absolutely.
Yeah.
All right. Thank you so much. Bye.
Bye-bye.
So goodbye.